Good evening, everyone. Thank you for joining us today. We are Team XMOS, and today we'll be presenting our smart baby monitor with integrated white noise machine. Our technical directors for this project were Dr. Andrew Kavanaugh, as well as Stephen Enzvino. Our team was composed of 2 electrical engineers, myself, Kieran Thacker, as well as Jake Mueller, as well as 2 computer engineers, Tevin Flores and Isaac Sosa. XMOS is a fabless semiconductor company based out of Bristol, UK. They specialize in developing audio products such as MEMS microphones, as well as multi-controllers such as the xcore.ai chip used in this project. This then brings us to our project motivation, which is to utilize the newly developed xcore.ai chip, which is a hardware-accelerated AI multi-controller for specific applications in Internet of Things. As a result, our project essentially seeks to utilize the underutilized technology of the xcore.ai chip to develop a non-internet connected IoT device. Our anticipated best outcome, or ABO, for this project was to then develop a daughter board that could be utilized by the xcore.ai chip. This would then be used to develop a commercial and smart baby monitor with key features that included a full duplex communication system, an alert system, crying detection using machine learning, and even a white noise machine. However, one of the biggest features would be that unlike other IoT devices, the xcore.ai doesn't rely on third-party services or cloud storage, essentially allowing all data to be kept local and private. Unfortunately, our team was unable to achieve our ABO. On the hardware side, the daughter board is currently non-functional, still requiring addressing using I2C to the audio codec, as well as troubleshooting of the buck converter chip, powering the main audio codec and temperature sensor ICs. On the software side, the machine learning model requires some updates and functions, as well as some current debugging in the autocontroller and the xcore tools. Despite this, our team was able to make some major technical accomplishments over the course of the semester, the first of which being the development of the Talkie Pi, or the Raspberry walkie-talkie, which introduced us to the idea of half duplexing and full duplexing in data transmission systems. From there, we familiarized ourselves with the I2S protocol using a digital to analog converter, which would then be applied to the audio codec. After this, we were able to evaluate the gains and distortion of some commercial speakers using the DAC, and following that, we began designing the audio codec and power supply systems for the daughter board. Finally, our last steps in this process were populating our PCB and developing our daughter board for the baby monitor. Pictured here is an image of the test signals used to evaluate our commercial speakers, with narrowband signals ranging from 100 Hz to 7 kHz, and the final broadband signals including a chirp signal and a complete white noise signal. This experiment essentially allowed us to evaluate the ideal commercial speaker for our baby monitor by analyzing which speaker had the least distortion with the highest gain for the baby monitor. Additionally, it allowed us to gain a better understanding of I2S protocol, which could then be implemented into the audio codec used for the baby monitor. And last but not least, our final key technical accomplishment for hardware was, of course, the design of the daughter board. This daughter board was designed in Altium and was originally designed as a 2-layer board for means of easier manufacturing and prototyping. And we also designed this with the 0805 package size in mind for easier board population as well. For the audio codec, we used the WM8960 it's a commercial audio codec, as well as a digital temperature and humidity sensor. And for the power supply, we used a 5-volt USB-C, which was then converted to 3.3 volts using a buck converter. Moving on to key technical accomplishments for software, our computer engineers were responsible for the software aspect of this project, and as such they worked on things such as audio streaming and the communication between the two boards, as well as acquiring data for our machine learning models. In terms of economic impact for XMOS, the Smart Baby Monitor provides an application of the existing xcore.ai chip and utilizes multiple features in doing so. This device provides the connectivity of an IoT device while protecting user privacy and data, and it combines the functionality of a white noise machine, a traditional baby monitor, and machine learning and AI modeling within the same device. By doing so, this project seeks to establish XMOS as a leader in privacy-respecting smart devices. Next, I'll be discussing a bit more about my technical individual contributions throughout the past year. So in terms of individual technical contributions this semester, aside from the Talkie Pi, I also prototyped the speaker system used by the Digital to Analog Converter Breakout Board, or DAC. This circuit was also used to evaluate the 3 commercial speakers that we're analyzing, and it was important because this introduced us to the I2S protocol, which is what we later used to select our audio codec. So in performing our experiment, we learned how to use Audacity, and furthermore learned a bit about analyzing spectrograms by specifically analyzing the spectrograms of the noise developed for each speaker, and that's what allowed us to select the speaker for our system. Once we had selected our audio codec, I began designing that portion of the board, where I specifically was able to learn more about various methods of filtering, and specifically RL filtering for the individual speakers and speaker systems. Additionally, I also implemented a temperature and humidity sensor for the monitoring of the ambient conditions of the environment that the baby monitor would be in. Moving on to individual technical contributions this semester. Once the PCB schematic for the circuit had been finally realized, we then began working on developing the PCB footprint layout. Here you can see in Figure 2 the PCB footprint layout for the audio codec and temperature and humidity sensor circuits that I designed. Once the daughter board footprint had been finalized, we then ordered the board as well as all the components, and utilizing the biomedical engineering lab Volterra PCB machine, we were able to populate and develop the boards. Once our boards were developed, we began by evaluating and testing the onboard power supply. This composed mainly of the buck converter chip and the USB-C chip. In troubleshooting the power supply, we determined the buck converter was unable to output the proper analog and digital voltage as designed. Once our issue with the power supply were realized, using a benchtop power supply, we were able to begin troubleshooting the audio codec and humidity sensor. Fortunately, the temperature and humidity sensor and audio codec were designed with onboard status LEDs, which indicated the ICs were being powered. However, unfortunately due to design error, the daughter board was missing the correct I2C pins for addressing to the audio codec. This concludes my technical contributions. Next, you'll be hearing from my fellow electrical engineer, Jake Mueller, and his accomplishments working with me in hardware.
Hello everyone, my name is Jake, and today I'm here to walk through with you all some of the things I was able to accomplish for XMOS this year. We started the year off by developing narrowband and broadband signals, then analyzing and comparing these signals to gain a better understanding of these signals. We decided to test these signals initially in Edwards Auditorium, but due to complications with the ambient noise and availability, we decided to test in Kirk Auditorium after class hours. All of our tests were conducted using 3 different speakers, each speaker being tested 9 feet away from the XMOS microarray. After completing testing in Kirk Auditorium with each of the 3 different speakers, I next developed the power supply schematic for our prototype baby monitor, which had to be designed in parallel with our audio codec. To power the codec, multiple 3.3 and 5 volt inputs would need to be satisfied with their respective voltage input, which motivated me to select the buck converter chip I did. Following the completion of the audio codec and power supply schematics, our next step was to integrate both designs onto the daughterboard PCB. To start the PCB design, we first had to select our component size. For our board, we ended up selecting 0805 as our primary component size. For the buck converter chip, I ended up selecting a 0706 package size, which proved to be troublesome. When populating the board in the BME lab, we were unable to place the buck converter chip due to its smaller package size, as it proved to be a problem for us to accurately place the component onto the PCB. Since we were unable to place the buck converter chip properly, we were unable to power the audio codec using the power supply and had to resort to other means to power the board. To power the board during testing, due to complications from the buck converter chip, we ended up using a signal generator to simulate the 3.3 volt and 5 volt inputs that the audio codec needed and powered it directly. Once the board was powered, we were able to verify that the audio codec was in fact receiving power, but unfortunately we were unable to test that the codec was functional due to complications with the I2C input not being populated on the board. That concludes what I was able to accomplish this semester while working under XMOS. With that, I will now let Tevin explain to you some of the things the software side has been able to accomplish this year.
Thank you for the introduction. My technical contributions were testing the Explorer board project, checking all of its features, such as connecting to a Wi-Fi network, using the microphone array to send audio to a host computer. Later on, we found out that this same feature was also supposed to send audio to the DAC, however, that wasn't working properly. And then we ended up isolating the project with some of the features needed for the ABO, such as connecting the board to a Wi-Fi network, using the microphone array to send audio to a host computer or another device. I also ended up learning FreeRTOS API, since it was essential in order to develop other features, such as being able to receive audio through TCP, sending the audio to the DAC so it can play. Moving on, I learned Python programming, things such as TensorFlow Python, TensorFlow Lite, NumPy, libraries related to audio. And then I ended up proceeding to acquire our dataset of approximately 402nd samples. I created multiple models. The first model was able to differentiate 4 types of noises, such as cry, laugh, silence, noise. However, I needed to consider the memory available on the Osprey board, so I decided to use the version that can only differentiate if the baby is crying or not. In general, the model takes a spectrogram as its input. It has 2 different outputs, crying or not crying. And now I would like to introduce Isaac Sosa to you all.
As part of our initial research into the baby monitor project, our technical directors, Andrew and Steven, suggested that we should look at the Talkie-Pi. And the Talkie-Pi is a Raspberry Pi based walkie-talkie which needs a kind of host system to host a server to allow the walkie-talkies to talk to each other. So what I did is I built one of these Talkie-Pis just by installing the necessary software off of GitHub and putting those things together, and also set up a Mumble server to allow audio communication between the Talkie-Pis. And also, to make sure that everything worked, just ran it on my laptop, server on the laptop, and just had the Raspberry Pis talk to each other, make sure voice communication was working.
The majority of the work that I've done on this project is on the programming side, and for that I built and tested the example Explorer board project, and that was to demonstrate most of the features that the Explorer board has, so like Wi-Fi and other features like that. I learned the FreeRTOS API to write applications for the actual Explorer board, as that's what the example code was written in. I discovered a lot of issues with the example code base. There's an audio receiving portion of that project, but it wasn't exactly working very well, so I went around and went to go fixing that. And also I created a custom project with only the necessary code for the actual our baby monitor project, so that has the audio receive code, the Wi-Fi stuff, drivers for all the other necessary hardware. And in this custom project, I got the audio receiving code to work for the most part, and I also modified the audio send code, which would take audio from the microphones and send it to the network to connect to another remote host so it can stream audio there automatically instead of having to connect to the board to get the audio from it. While I didn't do any work on the machine learning part, I also needed to understand how everything was working on that section of the project. So I learned the Google Machine Learning Crash course. I finished that, and that taught the basics of machine learning, taught you Python programming. I taught the TensorFlow API, NumPy, and also Pandas to do a lot of the numerical calculations that is required for machine learning. Our team would like to thank Dr. Sunak for helping Capstone being put together and making sure that we could actually have this great opportunity. We'd like to thank our technical directors, Andrew and Steven, for being there for us whenever we needed help and just kind of providing overall guidance. And also want to thank Mike Smith, Professor Young, and Joseph Reyes for helping out our electrical engineering students go through all the problems that we've had with circuit designs and PCB designs and advising them with that.